Hi everyone, so we're going to look at some work on friction and introducing frictional forces into our mechanics questions. So the first thing we need to look at is a couple of definitions. So if a surface is rough, and this is the word that we're going to be looking for in questions, so if it's smooth, then there's no frictional force. If it's rough, then a resistive force called friction acts parallel to whichever surface we're in contact with in the direction of the motion, and it always acts against the direction of the motion. It's a resistive force. So when surfaces are rough, a body will only move if the applied force on that body is greater than the frictional force. So frictional force builds up and up and up until it's overcome. So frictional force, and sometimes people make this mistake, it has this maximum possible value or a limiting value called F max. And that's equal to mu r, and we'll talk about those letters in a second. But it's really important we get our heads around the idea that friction does not have to build up to this full value, but that this is the limit that it can possibly be. And once friction max, F max, is overcome, once the force acting on the body trying to move it overcomes that F max, if it's larger than that, then the body will start to move. But until that point, friction will just build up and up and up. You know, you're trying to move this thing across the surface and the frictional force is building up and up and up until it reaches its maximum. And then if we overcome it, we move. So R we've seen before is our normal reaction force, and mu is what's called the coefficient of friction. And this is different between different surfaces in contact. It depends on the material that they're made up from. And mu will be higher for rougher surfaces and lower for smoother surfaces. And mu is equal to 0 if we have a perfectly smooth surface. So let's have a look at some examples of this. And today is just really an introduction to using friction and to getting used to practicing using frictional forces. And then next lesson, we'll have a look at applying friction to quite a few more difficult questions. So here's our first example. This is taken from the textbook actually. But it's quite a good illustration of this idea that friction only has to build up to the amount needed to stop the body moving, and it can only get high as F max, which is equal to mu r. So let's look at this. A block of mass 5 kilograms lies on rough horizontal ground. So there's that word that we're looking for in the questions. That means straight away friction is going to be involved. The coefficient of friction, so mu is equal to 0.4, and we've got a horizontal force applied to the block, so that's trying to move the block. And this question is saying, find the magnitude of the frictional force acting on the block and the acceleration of the block when this applied force is these different values. So we've got 3 different situations. So let's draw a diagram for each of these. So we've got our block of mass 5 kilograms, so 5g is our weight. We've got horizontal force applied to the block. So if I'm saying I'm moving to the right, there's my force P. We've got friction because it's rough, and that's going to be acting at the surface, resisting the force. So there's my friction. I'll call that FR for friction. And the coefficient of friction between these two surfaces, between the block and the ground, is 0.4. Okay. So let's just look at our force diagram. Straight away, I can see I need to add my reaction force on. So don't forget to do that. Quite often the diagram's not given, or if it is, they won't put the reaction force on for you. But it's really important here because obviously our formula for F max involves this. So the first thing to do in these questions is to actually work out what is the maximum possible frictional force here. So let's have a look at that. So what is the maximum possible frictional force? Well, that's F max, which is equal to mu r. And let's just have a look here. We know that mu is equal to 0.4, and our reaction force here isn't always equal to the weight, depends on what other forces are acting, but here, because there's nothing happening vertically, so vertically, if I look at that, what's going to happen? I've got r minus 5g. There's no motion in this direction, so that resultant force is going to be 0, so r is equal to 5g. So my F max is going to be 0.4 times my 5g. So that's 19.6. So 19.6 is my maximum frictional force here, but it's definitely the maximum. So let's have a look at each of these different situations. So looking horizontally then, so we want to get friction and this applied force P involved. So horizontally, I'm taking to the right as positive. So P minus that frictional force is going to be equal to, so this is resultant force equals MA. So P minus FR is going to be equal to 5, the mass, times the acceleration. Okay, so that's our first thing to look at here. So this is going to help us find the acceleration in each of these situations. But we need to know what this friction is, okay, because this is only going to be 19.6 if that's what's needed. So let's have a look here. So first of all, this force moving forward is 10 newtons. So that means that the friction only needs to build up to 10 newtons here to stop the motion happening. So for this to be equal to 0, my 10, so P is equal to 10, it hasn't built up to the maximum friction that needs to be overcome, so friction is going to build up to that 10 newtons as well, and then there won't be any resultant acceleration. There's no resultant movement then, the thing is still stuck because friction hasn't been overcome. It's built up to 10 and then the whole situation's just stopped. I'm not putting enough pulling force on this. So the resultant acceleration in that case is 0, friction's 10, resultant acceleration 0. Okay, let's have a look at part B. So part B now says my frictional force, says my forward force, my applied force is 19.6. And again, if we look at that, 19.6 minus my frictional force, well, my frictional force can only get up to 19.6, so that's what's going to happen here. The friction's going to build right up to 19.6. And then my resultant force equation is going to give me 19.6 minus 19.6. So again, here, the resultant acceleration is going to be equal to 0. And at this point, we call this limiting equilibrium, because what's happening here is your forward force and your F max are equal to each other, but the friction has built up to its maximum. So this thing, if I applied any force bigger than this, so even if I just went really, really slightly, a little extra push, this is definitely going to move. So at this point, this is kind of on the point of limiting equilibrium. The force applied, P, is pulling in one direction, the friction is opposing it, and we've reached that point where the friction can't go any higher. So if this force increases at all, the thing's going to start moving, but I'm at that kind of point, that limiting point where it's just about to go. Okay. Part C then, we've got P is equal to 30 newtons, and now what's happened? Well, my 30 is definitely bigger than my F max, so there's definitely going to be some movement now. And if we look at this, and we just need to be careful, the friction is not going to build up to 30, it can't. We can only get up to my maximum friction. So my maximum friction must have been reached. And now let's have a look at my resultant force. So now 30 minus my 19.6 is going to be equal to 5A. So in this particular situation, let's just sort that out on the calculator. So 30 minus 19.6, and then I'm going to divide that by 5. So that's given me 2.08 meters per second squared. So we've got the three situations there. One, where nothing's happening at all, the friction only needs to build up to 10, it's not going to reach its maximum, so the thing's at rest still. This one, where then F max, F max is reached because the force in this direction is as big as this, so this can get up to this maximum force. Now it can't go any more, but on this point of moving, okay? So this one is no movement. This one is limiting equilibrium. And then this third example, friction max has been overcome because the applied force is bigger than the maximum friction you can have. And so then we're going to get this situation happening here. I'm just going to explain that last couple of bits again because I can see here that I've moved down out of the screen a little bit. So I'm just going to move up there and I'm just going to go through these last two bits again, I think, because I don't know that you could see those. I'm sorry about that. So in this first situation, P was 10. Friction only needs to build up to 10. And then 10 minus 10 is 0. Resultant acceleration is 0. There's no movement going on here. The friction hasn't been overcome. In the second one, forward force is 19.6. So the friction is going to build up and build up and build up. It can only build up to 19.6 though. So that's what it'll do. It'll build up to 19.6. Can't get any more than that. But my applied force is not enough to overcome it. So 19.6 minus 19.6 is 0. My resultant acceleration is 0. And this is the one that's called limiting equilibrium. It's about to move. It's just on that point where friction is about to be overcome. And any extra force on P would make the thing move. And the last situation then here is where P is 30. And in this situation, friction doesn't build up to 30. Friction can't build up to any more than 19.6. So in this situation now, the friction has been overcome. The system is going to move. And then let's have a look at our resultant force. P minus friction max this time is equal to 5A. Rearranging that, doing it on our calculator, we get the acceleration is 2.08. So here, friction has been overcome. And we get a resultant movement in that right direction. So I'm sorry about that, messing about moving them up, but there's our three initial examples. I'm going to do another couple of examples on the next video, and then I'm giving you some questions to do on this today.